Okay, folks, we're continuing on with the application problems in section 6.5. This one is the classic half-life problem repackaged in a scenario that is very real. This is about me consuming a huge amount of cookies in a very short amount of time. So I'll let you read the problem here about my serious sweet tooth, and what the most important piece of information in this problem statement is this. The half-life of the cookies is 6 hours. That means no matter what quantity of cookies start in the house, whether it's 10 cookies or 100 cookies or 1,000, means 6 hours later I've eaten half of them. That's what is meant by half-life. So that's how we have to approach this problem, and the equation we're going to need is this guy right here. The quantity of a product at time t is equal to an initial amount times e raised to the kt power. Now, if you go back and look at the half-life page that you picked up in class, I think you may see another alternative form of this that we talked about, which looks something like this. The amount after time t equals some initial amount times 1/2 raised to the t over n, where n is the number of half-lives. This is a way more convenient form of the half-life equation to use than the one that involves e, the base of the natural logarithm. However, I'm going to discourage you from using this and encourage you to use this one for reasons that will become clear over a year from now when we get into the differential equations portion of AP Calculus. So I do want you to be using this form of the equation. Okay, so part A of this problem says determine an equation in base E, so I have to use this form, for the amount of cookies remaining in Mr. Vass's house from an initial amount as a function of time. Make sure you solve for K. Okay, so that's what our goal here is. We're going to solve for K. So I'm just going to go ahead and rewrite this equation. A of t equals A sub 0 times e to the kt. Let's just say that the initial amount is, I don't know, how about 100? Well, after one half-life, there would only be 50 cookies left. And that half-life is 6 hours. So I've substituted in the quantities in this equation that I know. I know the half-life is 6 hours, so that's t. I also just picked an arbitrary initial amount of 100. You can pick any value you want there, just as long as the ratio of this number to this number is 1 to 2. Because what happens next is really where the magic happens in this problem. If I divide both sides by 100, here's what we get. We get 1/2 equals e to the 6k. Now I can solve for k, which is what I was asked to do right here. How are we going to solve for k? Well, I see an unknown. I'm looking for k, and it's up in the exponent, so I'm going to need a logarithm. I'm going to take the natural log of both sides. So I have the natural log of 1/2 on the left equals the natural log of e to the 6k. If you recall our power property of exponents, we can rewrite the right-hand side as 6k times the ln of e. And by now, I know that you all know the natural log of e is equal to 1. So I'm ready to solve for k. The constant k is going to equal the natural log of 1/2 divided by 6. Okay, now if you want to go ahead and plug that into your calculator, you can get an approximate value. So k is about equal to negative 0.1155. So the final answer here, we found k. My final answer is the equation for the amount after time t is some initial amount times e to the negative 0.1155 times t. So any amount of cookies that are brought into my home, that's a sub 0. I can use that in this function to determine or predict an amount after time t. Okay, let's move into part B. Mrs. Vass brought home some cookies from the store. 30½ hours later, there were only 3 cookies left. How many did Mr. Vass eat? Well, we're going to have to go back to our equation here that we just derived in the previous step. The amount after time t equals the initial amount times e to the negative 0.1155 times t. So what do we know? Well, we know t is 30½ hours, and there were only 3 cookies left. So this is going to be 3 equals some initial amount times e to the negative 0.1155 times 30.5. Now, folks, I know this equation looks really scary, but it's not as scary as you think. I have the left-hand side is the number 3. The right-hand side is a0, that's the initial amount that I'm looking for, times this. That's just a number. It's e, or about 2.7182, raised to the negative 0.1155 times 30.5. So I'm going to go ahead and rewrite this equation, solving for a0. a0 equals the number 3 divided by e raised to the negative 0.1155 times 30.5. And when you run that through your calculator, you're going to get an initial amount of 101 cookies. That is quite an impressive feat, to eat or to start with 101 cookies, and after 30½ hours only have 3 left. Incredible. So how many did I eat? Well, we haven't answered the question yet. I know we're still stunned by this number and wondering, how is he still walking? But to answer this question, we have to look at the initial amount and the remaining amount and do a little subtraction. So 101 minus 3 gives us an answer of 98 cookies. That's the amount that he consumed. Moving on to question 3, trying to get in the holiday spirit here, we're going to work on a problem involving a Thanksgiving turkey. And we've got some key numbers to highlight in this problem. I usually cook my bird to an internal temperature of 180 degrees Fahrenheit. Of course, that's measured in the thigh. One year I even measured the rate of cooling for the bird. Amazingly, after it was removed from the oven, it cooled to 175 degrees Fahrenheit, or it lost 5 degrees of temperature in 12 minutes. I also keep my house set at 70 degrees Fahrenheit. So this is the classic Newton's law of cooling problem, and here's the formula for that. So part A of this problem, after I take a look here at the Newton's law of cooling formula, it says that the temperature at time t is equal to ambient temperature plus the difference of initial temperature, that's T sub 0, minus ambient temperature times e to the negative kt. Okay, so part A says express the temperature of the bird T as a function of time T in minutes. Well, here's the formula. We just have to figure out what we already know and what we still have to find out. So I think we can identify some of our highlighted quantities here. 170 degrees, that's equal to ambient temperature. That's the temperature in the house. T sub 0, that's 180 degrees Fahrenheit. That's our initial temperature. So if we look back at the Newton's law of cooling formula, we know T sub A, we know T sub 0, we also know T sub A. E is the base of the natural logarithm. T is our variable. What we don't know is K. If only we could find K. Well, perhaps we can. We haven't used this number of 175 degrees Fahrenheit. Well, that's T of 12. That's at 12 minutes after the turkey's removed from the oven. It's cooled to 175. So if I use that value, it's, you could think of it like an ordered pair. In this case, we have at minute 12, we have a temperature of 175. Think of it like an ordered pair. We can use that point on the graph of this function to find out what k is. And we're going to go ahead and set that up as follows. So once I substitute my known quantities into the function for temperature, I have this equation here. I'm going to start by, again, we're trying to get k all by itself, and k is up in an exponent, so yeah, we're going to need a logarithm, but we have a lot of simplification to do first. First thing I'm going to do is get rid of the 70. This 70 is added to this quantity, so I can subtract that 70 from both sides. And when I do that, I'm going to get 105 equals this thing here. Now 180 minus 70, that's 110. And then I have e to the negative 12k. Well, at this point, I can get the k a little bit more by itself if I divide both sides by 110. What I have now is 105 divided by 110 equals e to the negative 12k. As I've mentioned several times, anytime you have a variable, in this case k, in your exponent, you need a logarithm to isolate that. I'm going to go ahead and do that now. I'm going to take the natural log of both sides, and I get the natural log of 105 over 110 equals negative 12k times the natural log of e. Folks, I skipped some steps there. I really did. I hope that's okay. I hope you can see that when I take the natural log of this, I can use the power property to take negative 12k outside of the logarithm. I hope you also recognize by now that the natural log of e is 1. So I'm ready to isolate k and write that k equals the natural log of 105 divided by 110, all divided by negative 12. After you run this calculation through your calculator, you're going to get k equals approximately 0.00. Oh, folks, you deserve better than that. Let me give you a better number there. Approximately 0.003877. We're now ready to write our temperature function. We were asked to express the temperature of the bird as a function of time. And we've got that because we now know what k is. So temperature as a function of time is equal to 70 plus 180 minus 70, which is 110, times e to the negative k, 0.003877 t. Final answer. Okay, moving on to part B. Final part of this problem. Final part of our little pre-holiday festival here. Ideally, a turkey should rest for at least 30 minutes prior to carving. What will the bird's temperature be after 30 minutes? Folks, this is a straight plug and chug problem. You're going to need to plug in 30 minutes where you see t, and you're going to get the following. You're going to get t of 30 equals 70 plus 110 times e to the negative 0.003877 times 30, and that's approximately equal to 167.9 degrees Fahrenheit, perfect serving temperature for your holiday turkey. Okay, folks, one thing I do want to point out about this problem is everything we did in this problem was in degrees Fahrenheit and minutes. How might somebody try and trick you in one of these problems? Well, what if they give you everything in minutes and then they ask you about something with respect to an hour? Like, let's say I said ideally the turkey should rest for at least a quarter hour prior to carving. Should you put 1/4 in here? No, you should put in 15, because 15 minutes is 1/4 hour, and our initial function was in terms of t in minutes. So make sure you don't let anybody trick you by giving you a time that's not the same as the units of time you used at the start of the problem.